Okay, so hi, good afternoon, everyone. You can hear me well, right? Yeah. So I'm Cristina. I've been working at the UNSW for the past 3 weeks. So today I'm going to be showing you the work I've been doing together with Sarah Broff and also Mireia Montes. She's one of our main collaborators in Spain at the IAC. And then we have a group of very nice collaborators even here in Australia and overseas. So I'm going to show you our nice project about how we made it to analyze the Intra-Group Light in a group of galaxies and which are our plans and our current work regarding that. So first of all, let's go to the beginning. What is this Intra-Group Light? So it is basically a large region of faint and diffuse light that we find in the center of groups. This light is coming or is made by the stars that were unbound from their host galaxy due to interactions. So it is kind of a fossil record of all the interactions that a group or a dense environment has been suffering throughout its whole life. Here you can see an image, and actually this faint light, I don't know if you can see it very well in the projector, but there is like a faint light kind of around all the galaxies in this group. And why is important, this intra-group light? Well, as I said, it's kind of a fossil record of all the emerging history of a group. So it is a great tracer of the mass assembly history of these environments, not only for groups, but also for clusters. Actually, in simulations of the growth of the BCG, of the brightest central galaxy, when they include that a percentage or an amount of the stars that were supposed to end in the BCG, they actually end up in this diffuse component, they reach a better agreement with observations. This is one of these simulations I'm talking about. The IGL is also key to understand the ICL, the intracluster light, basically because galaxies spend most of their lives in groups, so the groups are then the building blocks for more massive and complex clusters. And actually, in simulations and some analytical models, they have found that up to 30% of the intracluster light in simulations comes from the pre-processing of the intra-group light in groups, in the groups stage. However, this light is very faint, so it's very hard to detect. You start seeing it, detecting it beyond 26 magnitudes per second square. It's also very extended, and the light distribution depends a lot on the environment, on the properties of the group. So it's very hard to detect, and this is the main reason why there are very limited studies so far. Most of these studies have been in dense and strong environments, such as compact groups. Also, there are a few detections in loose groups of galaxies, but in general, massive ones. And in most of the cases, all this work has been done in nearby systems. On top of that, we found that when we plot our results, the amount of faint component that we find, either in groups or in clusters, when we plot this amount of light over the total light of the system as a function of the redshift, as you can see here, all the observational results that we have, these are shown here with the gray points, they show a large scatter from almost 0 to 40% of diffuse component in the system, and they do not agree with the theoretical predictions, which are, two examples of them are these purple and blue regions that you can see. They predict that the diffuse component should increase with time, and we do not see this yet. So what we need is two main things. First of all, to establish a common way to define and to measure the intragroup light and also the intracluster light, because most of these points, they come from different techniques, different wavelengths as well, different resolution, depth, and even different systems, of course, with different mass, redshift, environmental conditions, etc. And of course, we also need larger samples. So our work tries to to solve, well, not to solve, but to help to solve this problem. And what we have done is to select a sample of groups of galaxies. So we have a sample towards the low mass regime, which is part of the main problem that we have before. Most of the systems that have been studied before were massive ones. And also these groups are nicely distributed from close by up to 0.5 in redshift. One of the key points of our work is also that we are measuring always the same data, same wavelengths, and using the same method. And actually, this is the main point in which I'm going to be spending most of the talk, because so far what we have been doing is to develop this method with the aim of doing as much as automatic as possible, because as I said before, this light is very faint, very hard to detect, and very different depending on the system. So to do something automatic is very, very hard. So I've been trying to do that. And to test our method, we have selected or choose one of these groups. And we have done a pilot study to test the method and see if we actually are doing a good job and if it is actually working. Our data comes from the Hypersupreme CAM data release 2, because it's basically the deepest optical survey that we have so far, and also because the pipeline is a custom version of that of the LSST that is going to be implemented in the LSST. So both surveys share same structure and similar data products. So then it's going to be quite easy for us to study this huge amount of data that we are going to have from the LSST. And then we also use gamma catalogs to have the physical information of the galaxies in the group and the groups, such as mass, redshift, position, even in the sky, some other properties that we need for our analysis. So let's take a look to our pilot group. It is composed by 6 galaxies. These are labeled here in white with the white long numbers. It is located at redshift 0.2, and as you can see, there are many things, many sources that are making our life quite difficult. There are a few bright stars labeled as S1, 2, and 3, foreground and background objects all around, including some foreground galaxies that are falling on top of our intra-group light and very close to our galaxy members. So we basically have to get rid of all of that light and just have our intra-group light to be analyzed. And this is what we do with our method. This is a reduced image from HSC as it comes from the archive. And what we do with our method is to reevaluate the sky background emission, model and subtract the bright stars, accounting for the PSF effect, model and subtract the galaxies in our group, accounting also for the PSF effect and its extended wings as well, and then mask every other background foreground object that we have. So by doing that, we get our IGL only emission. So let's do this again. So you can see the difference. And here we nicely, we can even see that there is, I don't know if you can see it here, well, just a bit, kind of a tail substructure towards the right side of the core of the group. And the residuals here in the center are very minimal, the residuals from the subtraction of the galaxies of the group. So we were quite happy with this, and actually we reached a suffer brightness limit of almost 31 magnitudes per second square in G-band, which is great and very similar to what the LSST is going to reach after 10 years observing. So let's study this beautiful IGL. The first thing that we did was to extract suffer brightness profiles from the IGL. These are shown here with dashed lines in the 3 bands that we are analyzing, G, R, and I band. And also we compare it with the profiles extracted for the whole group, for the whole group of galaxies. So in this way, we can see where the IGL starts to be the dominant component and also evaluate PSF effects and etc. But the main point here is that we are able to have reliable detections of the IGL, and actually not only that, but also we got the most extended intra-group light detection up to date, reaching around 250 kiloparsec from the center of the group, while the most extended ones before reached around 160. So this was something that we didn't expect, so we were happy to have this nice result as well. We also studied the stellar populations, and we did a color analysis of the stellar population in the group by getting the mean color value for the intra-group light component, and then shown here with the green triangle, and then the black square is the mean color value for the galaxies we have in the core of the group, the ones that are on top, like within the center of the IGL. We find we have it here in this color diagram on top of the stellar age and metallicity tracks to have an idea of the age and metallicity as well, finding that the IGL is younger and less metal-rich than the 3 BCGs, let's say, that we have in the core of the group. This is in agreement with theoretical predictions and some observations before in intra-group light and intra-cluster light as well. And actually, by taking a closer look to these values, we find that the metallicity of the intra-group light is similar to that that we find in the outer part of these galaxies, similar to the Milky Way, and also is similar to this galaxy member. Oh, sorry. Okay. It's similar to this galaxy member that we have here. This is a member of the group, and it seems to be the galaxy that has produced this tail towards the right side of the intra-group light, and also the metallicity in its outer parts is very similar to that of the IGL. So putting all that together, we propose, or we think that the main information driver of this IGL is the tidal stripping of massive satellite disk galaxies, like partial stripping, which means only the outer parts of the disk, the stars in the outer parts of the disk. So finally, we also measured the intra-group light, which, as I said at the beginning, is the amount of intra-group light that we have in comparison, or the ratio between the amount of did this using 2 different methods. One is the Suffer brightness cut, which is basically to say, okay, from this Suffer brightness value, usually 26.5 magnitudes per second square, from this and fainter, every light that it is fainter than this is going to be our intra-group light. And then the other value is to directly measure all the intra-group light from the image I showed you before. It is called composite model because this light was obtained after modeling and subtracting the galaxies in the group itself. Our points agree well with previous observations. In this plot here, plotted as a function of the redshift. Here we have groups and clusters both. But as I said, we still need more data points here in order to see if there is any kind of correlation with the amount of intra-group light and the redshift, and also the mass. So this is what we plan to do, and keep going. Now that we are sure that our method is working, we are now starting to work on measuring, repeating the process for the whole set of group galaxies that I showed at the very beginning. So I'm going to finish here with the take-home message. Basically, we have done a pilot study with one group to test our method. We have been able to measure this intra-group light. Actually, it has been the most extended up to date, finding that it is younger and less metal-rich than the galaxies in the core, and probably formed due to partial tidal stripping of massive disk satellite galaxies. We need more data to find any kind of correlation or not with redshift and with mass, and this is what we are doing right now by adding more analysis using more groups. So thank you so much.